If you've ever, spent hours mapping out the perfect schedule for your week, you definitely know the feeling. Every hour is color-coded, every task is optimized. It looks, well, brilliant on your screen. And then Monday morning reality hits.
Oh, exactly. The car won't start, or a critical meeting runs 20 minutes over, and suddenly that beautiful, perfect plan is just a complete fantasy.
Right. And in the corporate world, there's actually a very specific name for this phenomenon. It's called the execution gap. It's that massive void between a theoretical, mathematically perfect plan and the chaotic physical reality.
Yeah, and nowhere is that execution gap more expensive or honestly more volatile than in the global supply chain.
For sure. So for today's deep dive, we're looking at a stack of documents, case studies, and presentations from a company called Provision A. The mission today is to really uncover how artificial intelligence is stepping into that execution gap and just completely rewriting the rules of logistics.
Right, because we are moving away from systems that just tell supply chain managers what theoretically should happen to systems that actually, manipulate the physical world to make it happen.
Yeah. But to understand how this works, we have to start by defining the tools themselves. The industry throws the term digital twin around constantly. It's like the ultimate buzzword right now.
Oh, it's everywhere. But looking at the sources, it's pretty clear that a lot of companies claiming to have a digital twin are actually just running a simulation.
Right. People use them interchangeably, but I mean, a simulation is static, it's strategic. You use it in a design phase for a hypothetical what-if scenario. Like, if you want to figure out the optimal geographic location to build a brand new distribution center, you run a simulation based on historical labor rates and average transport costs. It doesn't require a physical counterpart or, live data feeds.
Exactly. A digital twin, on the other hand, is a living, virtual replica of a physical entity. It continuously updates with real-world data, so IoT sensors on pallets, telematics from trucks, warehouse management system outputs across its entire life cycle.
The sources mention waste management, right? The massive trash hauler.
Yeah, they're a prime example. They utilize a digital twin for routing their fleet that they actually call Waze on steroids. It continuously ingests localized data to remap physical logistics on the fly.
See, and that distinction brings up a fascinating myth in the industry that the Provision I techs really dismantle. Because we hear living replica and continuous data, there's this expectation that a true digital twin absolutely must operate in instantaneous to the second real time.
Right. The theoretical ideal is that if a system monitors localized weather patterns and traffic, it can predict exactly how much ice cream is being sold at a corner store, and the exact second a carton is scanned at checkout, a signal is beamed to a factory to manufacture a replacement unit.
Which sounds amazing, but the reality is different.
It sounds great in a boardroom, yeah. But in physical logistics, instantaneous reaction is actually highly disruptive. Logistics events are discrete, physical actions governed by mass and physics. You cannot teleport a forklift.
Right.
So real-world platforms, like AutoScheduler, which is mentioned in the texts, they ingest truck arrival data from visibility providers like FourKites or Project 44, but they don't act on it the second a truck gets delayed by a traffic light. They use that data to adjust warehouse dock times on a short-cycle cadence. And usually, that cadence is about every 30 minutes.
Wait, 30 minutes? I mean, if my GPS map only updated every 30 miles on a road trip, I would miss my exit entirely. How is intentionally building a 30-minute lag into the system not just creating a different kind of chaos?
Well, you have to think about the physics and the human element of a warehouse floor. When you apply optimization to a physical system, you need a moment of steady state.
Okay, what do you mean?
You need a defined batch of information to calculate the absolute best decision, not just the fastest decision. If a system reacts instantaneously to a truck reporting it will be 2 minutes late, and then immediately reroutes 3 forklift drivers to different docks to compensate, the resulting confusion just causes a massive butterfly effect.
Oh, I see.
Yeah, so the 30-minute cadence gathers enough data to see macro patterns rather than micro fluctuations, preventing chaotic overcorrection.
That makes a lot of sense, actually. You are optimizing the aggregate flow rather than like twitching at every single data point. Which leads to the core question, why do we even need this 30-minute digital twin in the first place? And I guess it all comes back to that beautifully laid, color-coded schedule.
The execution gap. Modern supply chains run on a complex, heavily siloed stack of enterprise software. You have the ERP handling orders and billing, the TMS managing transportation, the WMS running the warehouse, and at the very top, the APS, the advanced planning and scheduling system.
And these systems operate completely sequentially, right? Like the APS finishes its math, assumes the job is done, and basically just throws the plan over the wall to the next software layer.
Exactly. And the fatal flaw originates in that very first step with the APS. Supply planning systems are historically designed with a single overriding objective, which is to maximize customer service. They calculate how to ensure every customer gets exactly what they ordered.
Which sounds good on paper.
Right. But to solve that math problem, the software is forced to make a massive assumption that the company possesses infinite warehouse space, infinite labor, and infinite trucking capacity.
Wow.
The Provision A documents literally refer to this output as a mathematical fantasy.
So traditional planning is essentially like crafting a microscopic minute-by-minute itinerary for a massive cross-country road trip. But you never actually check if the car have a gas tank, or if the hotels along the route even have open rooms. You just assume the physical universe will bend to accommodate your spreadsheet.
That captures the absurdity of it perfectly. And compounding that fantasy is a severe visibility issue. Most human supply planners are operating with a horizon of about 7 to 10 days out.
Okay.
But average global supplier lead times are 37 days. So planners are working with a massive, nearly month-long blind spot where they simply cannot see the volume spikes coming.
Man, the sources actually feature a striking quote from a Fortune 50 VP of Transportation that distills the daily reality of this blind spot. He said, we ship at a premium cost a product that may not be needed from sites that may have difficulty shipping it to sites that struggle to receive it.
It's an incredibly costly feedback loop of failure. And the sheer computational volume makes manual intervention just impossible. The sources detail a time study where they placed a highly experienced supply planner in a simulated environment with just 50 part numbers.
Just 50.
Yeah, just 50. They asked the planner to find the shortages and identify the root causes. It took that expert 7.7 hours just to analyze those 50 parts. A typical global network has thousands, sometimes tens of thousands of parts.
So when the mathematical fantasy of traditional planning inevitably crashes into the physical bottlenecks of reality, you need a system that doesn't just raise a red warning flag, but actually intervenes to change the plan. And this is where the Provision A documents introduce level load, which they define as a prescriptive digital twin.
Right, and a prescriptive system fundamentally shifts the paradigm. Instead of predicting a bottleneck and waiting for a human to spend 8 hours fixing it, level load actively takes action. It ingests the data from demand forecasts, customer orders, carrier capacity constraints, and physical warehouse limits, and it simultaneously optimizes the entire network for the next 30 days. The guiding principle is to plan the flow before the spike.
And planning the flow requires holding your place in line because, well, transportation capacity isn't infinite. The text outline a very specific mechanism for this. Level load injects dummy codes directly into the ERP system days or even weeks in advance.
Exactly. Because demand is constantly shifting, you don't know exactly what products you'll need to ship on a specific Tuesday 3 weeks from now, but you know you will need a truck. The dummy codes reserve the flexible transportation capacity.
Then, as that Tuesday approaches and the actual demand materializes, Level Load's sister system called AutoO2 steps in. AutoO2 automatically replaces those placeholder dummy codes with real-time, demand-driven product allocations. It determines exactly what physical goods need to move today to satisfy the actual customer orders.
Right, but AutoO2 goes far beyond just generating a pick list of products. It actually engineers the physical execution of the load. This is where the digital twin interacts directly with the laws of physics.
Oh, like the volumetric mapping.
Yes. AutoO2 acts as a sophisticated constraint engine. It performs 3D volumetric mapping to physically build the load inside the software before a single box is ever touched on the warehouse floor. It calculates the center of gravity to ensure the trailer is axle legal, preventing hefty Department of Transportation fines or highway delays. It evaluates crush classes so that, a heavy pallet of liquid detergent isn't stacked on top of fragile paper goods.
That level of spatial engineering translates into massive financial leverage. The sources show that by optimizing the physical geometry of how the truck is loaded, companies save 4 to 8% in overall truck usage. I mean, if you shave 8% off your total trucking volume just by packing the trailer more intelligently, you've probably funded the entire technology upgrade in a matter of months.
Oh, absolutely. And the network-wide results are profound. The case studies document a 60% reduction in daily shipment variability. They achieved nearly 100% first tender acceptance, meaning the first freight carrier they contact accepts the job because the carrier knows the schedule is reliable and the load is legally viable. Yeah, and all of this cascades into roughly a 4% savings on deployment freight overall.
There's a specific analogy in the sources regarding network variability that stood out. They describe smoothing a supply chain as squeezing a balloon.
Right.
So if a traditional planner manually forces shipping volume down in one lane to fix a localized problem, that volume just pops up somewhere else, usually overwhelming a different distribution center. If level load is intervening to smooth out the spikes, how does it avoid just, transferring the chaos from Chicago to Atlanta?
Well, it avoids the balloon effect through concurrent network-wide optimization. When a human planner diverts trucks from Chicago to Atlanta, they lack the computational power to simultaneously analyze Atlanta's inbound schedule, labor availability, and dock door capacity for the next 30 days. They fix one node by breaking another.
They can't see everything.
Exactly. Because level load is a digital twin of the entire network, it sees the whole balloon at once. If it algorithmically slows down shipments to one site, it recalculates the flow across every other facility in real time, ensuring no single site exceeds its physical handling constraints.
That's incredible. So getting the transportation optimized and smoothing the flow over a 30-day horizon solves the macro-level execution gap. But the documents push further into the micro-level execution on the warehouse floor, detailing the evolution toward the agentic supply chain. And this isn't a proposal to just rip and replace all the legacy APS and ERP systems we just discussed, is it?
No, not at all. It's about wrapping those rigid sequential systems in an orchestration layer of intelligent agents. In this framework, an agent is an AI entity assigned a specific domain, equipped with the autonomy to perceive its environment, make decisions, and execute actions to achieve a defined goal. You establish a demand agent, a supply agent, a warehouse agent, a transport agent, and an overarching control tower.
But for those agents to be effective, they have to communicate and resolve conflicts. Like, if the transport agent schedules a truck for 2:00 p.m. to maximize fuel efficiency, but the warehouse agent knows the 2:00 p.m. shift is understaffed, they need a shared protocol to negotiate that conflict. Historically, systems communicate through APIs, but APIs are incredibly brittle. If a single data field changes format, the API breaks, and the systems just stop talking entirely.
Yes, and this is where large language models, or LLMs, transform the architecture. We typically think of LLMs as chatbots. But in an agentic supply chain, the LLM acts as a dynamic translation and negotiation layer. Instead of relying on a rigid, hard-coded API, these agents communicate intent and constraints using structured natural language.
That's wild.
Yeah, the LLM parses the unstructured reality of the warehouse floor and translates it into mathematical constraints the other agents can instantly process.
The sources highlight a deployment of this concept at Frito-Lay. They operate highly complex warehousing environments, integrating human workers and automated machinery. As discrete tasks are generated dynamically on the floor, an agent assesses the real-time state of the building. It negotiates the task requirements and routes the work either to human labor or to an autonomous machine right in the moment, constantly rebalancing the workload to prevent bottlenecks.
Exactly. It functions entirely as an orchestration layer, navigating complex constraints with the fluidity that traditional software simply cannot achieve.
But I imagine handing over multi-million-dollar physical operations to autonomous AI agents negotiating via language models triggers massive anxiety for supply chain executives.
Yeah.
I mean, the fear of an autonomous black box hallucinating a decision that shuts down a distribution center has to be very real.
It is, and the sources address this directly by emphasizing a tight human-AI loop. The goal of an agentic supply chain is not to remove human oversight. It's to offload the crushing volume of routine optimization. A human planner cannot calculate millions of mathematical permutations to balance an axle weight while simultaneously evaluating 30 days of labor schedules across 12 facilities. The AI agents handle the massive concurrent math, freeing the human operators to handle edge cases, strategic exceptions, and ultimate oversight. The human remains the pilot. The AI is just a radically advanced autopilot.
And the real-world impact of that autopilot extends far beyond operational efficiency and corporate profit margins. This brings us to the physical byproduct of all this mathematical precision, which is the environmental impact. The optimization required to bridge the execution gap directly tackles one of the most stubborn environmental challenges in the corporate world, Scope 3 transportation emissions.
That's right. Scope 3 emissions represent the indirect greenhouse gases produced in a company's value chain. For large-scale manufacturers and consumer goods companies, third-party transportation constitutes a massive percentage of their overall carbon footprint. You cannot meaningfully decarbonize a global enterprise without fixing the logistics network.
The environmental metrics tied to provisionized optimization tools are staggering. By enforcing prescriptive load building and smoothing out the volume spikes across the network, they eliminate 88,000 trucks from the road annually.
And the carbon math on that is highly significant. Eliminating those trucks equates to a reduction of 285,000 tons of CO2 per year across their client base. The text contextualized this by noting it's the equivalent of the carbon sequestered by 4,675 acres of mature U.S. forest every single year.
Wow.
Yeah, and this isn't achieved by purchasing carbon offsets. It is achieved by aligning the supply plan with physical reality.
Because when level load smooths out those chaotic spikes, companies are no longer forced into panic mode. They don't have to rely on last-minute high-emission spot trucks just to force a delayed product out the door. Predictable volume allows them to shift freight to lower carbon intermodal transport, seamlessly combining rail and trucking.
Exactly. It also systematically eliminates the hidden operational waste that burns massive amounts of diesel. Highly accurate, prescriptive planning drastically reduces deadhead mile situations where a truck is driving completely empty just to reach its next pickup location. Furthermore, by orchestrating exact arrival times through the digital twin, you eliminate dock idle time.
Right, because trucks aren't just sitting there.
Right. Trucks are no longer sitting in a staging yard for 48 hours with their engines idling, waiting for an overwhelmed warehouse to clear a dock door.
The sources feature a case study from Unilever that serves as the definitive proof of concept for this. Through this exact AI deployment, they achieved industry-leading truck utilization. We're so often conditioned to believe that corporate sustainability requires a massive green premium, that companies have to sacrifice margin to buy unproven technology or entirely new electric fleets. But this proves that operational efficiency and sustainability are actually the exact same mechanism. The most profitable route is inherently the one that burns the least fuel.
Exactly. You are systematically eliminating the physical waste created by the execution gap. The financial savings and the emission reductions are inextricably linked.
Oh, we've covered a massive amount of technical ground today for you all. We started by drawing the hard line between static, hypothetical simulations and living digital twins. We unpacked why the physics of a supply chain demands a 30-minute operational cadence rather than chaotic, instantaneous reactions. We explored how the mathematical fantasies of traditional APS planning create the execution gap, and how prescriptive tools like level load and auto O2 use advanced constraint engines to mathematically bridge that gap, planning the flow before the spike.
And from there, we looked at the architectural evolution toward the agentic supply chain, where intelligent, autonomous agents utilize LLMs to negotiate complex constraints in real time, effectively wrapping legacy software in a dynamic orchestration layer.
The overarching takeaway from these sources is that the most profound technological innovation doesn't always come in the form of a shiny new consumer gadget. Sometimes, the most world-changing innovation is applying brilliant mathematics and autonomous AI to the invisible, highly complex logistics networks that keep the global economy running, proving along the way that massive corporate profitability and aggressive decarbonization can actually go hand in hand.
It completely reframes how we think about complex systems. I mean, if agentic AI can successfully parse unstructured data to negotiate multivariable physical constraints, like balancing trailer axle weights, warehouse labor availability, and month-long transit times without breaking a sweat, it raises an incredibly compelling question for you to think about.
Ooh, I like where you're going with this.
What happens when we start applying these same autonomous negotiating agents to our own daily bottlenecked workflows? Imagine a suite of personalized agents dynamically orchestrating the chaos of your email inbox, negotiating conflicts on your calendar, or actively balancing the supply and demand of your own daily energy.
That's a powerful thought. If an orchestration layer can synchronize a global supply chain and eliminate 88,000 trucks from the road, well, maybe it can finally figure out how to keep a beautifully laid, color-coded Monday schedule from falling apart by noon. Thanks for joining us on this deep dive. We'll see you next time.